Hello, Darrell Lee Berry Jr. back for some more physics. I plan on continuing some reading of classical mechanics. I did a little bit off screen. I'll continue where I left off. Basically, I plan on asking my professor tomorrow. I plan on asking my professor tomorrow about this equation, um, 3/100. So, seems like there's some shenanigans going on here. Let me see here. Hold up. Like I said just now, as a matter of fact, I'm using a different notation system in the book. So I think just now I see what the uh, discrepancy is. No, actually, maybe not. So basically, what we're looking at is it looks like so this epsilon there is going to be the eccentricity, and we're looking at a scattering problem between two charges. So the Coulomb force is causing a repulsion. You have one stationary charge and one charge that's being projected into the field of the stationary charge. And 1 over r is a way to get the angle of nearest approach. So going back to the drawing that we looked at yesterday, this is the angle of nearest approach that I have highlighted in yellow. So looks like we're taking this and inserting epsilon and cosine. I can almost see it a little bit. This is my question, how to get 3100. But looking at this, if we have this, these two, and these squares, these squared, this will have a square. It will have a square. So at my Coulomb constant, the Q, my two charges, they're both positive or negative. The large Q is the stationary charge. So pretty sure there's an abbreviation for L. There must be a better way to do this though. L is that. So there's a lot of substitutions up in this thing. So that means that if I substitute that, try this a bit more before I move on. I have, right, so I'm going to take L away. And now I'm going to have S squared. I'm going to have E squared because E, when it comes out of the square root, it will multiply with that one. We have 2m, so we have 2 squared. 2 can go back under there, and m cancels out. Right. So you have this. So now we're getting closer to the book answer. You can see the book uses Z for the particle and E for the charge. And I just did it the normal way and used Q for the species and charge. Right, so we have this. And this looks to be what they have. 2ES over KEQQ. They absorb the constant of the Coulomb constant inside the uh, species. So what I'm seeing though is MKC Q over L squared 1 minus the eccentricity. I'm not going to use the E for eccentricity since I'm not using the E for the charge. So how do they get, oh, hold up, never mind. I was about to say it's something to do with cosine squared, but I won't do. All right, so I'm sure it's something small. I don't want to spend a whole lot of time on this. There's probably some small detail on the derivation, but I ask Professor tomorrow. But it's close. This E cosine. Okay, let's leave it alone. This hyperbolic orbit equation has the same form as the elliptic orbit equation except for a change in sign, the direction of the incoming asymptote. Psi, so we're going to be talking about this illustration here, where now we have a incident particle is being scattered by another particle of the same charge. There's a spread of the scattering angle, d theta. And now we have psi, which I believe, yeah, we have here. So they're saying cosine psi equals 1 over the eccentricity of the orbit. As r approaches infinity. And sine of capital theta over 2 equals 1 over eccentricity. They have cotangent big theta over 2. Oh, I see. They're using equation 3.99. Well, at least they're saying what equation they're using. Oh, and using equation 3.99. Yeah, so cotangent is sine over cosine. I hate the lack of explanation of things in this book, which is ironic, I think. So cosine psi equals 1 over e. sine big theta over 2 equals 1 over e. Hence, cotangent squared big theta over 2 equals e squared minus 1. I'm using the equation 3.99. And so that gives cotangent squared, this cotangent big theta over 2 equals 2 es over hmm, wow, they're separating the charge. In my notation, I would have Q like Z is the charge. We know it's going to be positive, either two positive charges or two negative charges because they're repelling. So I could just put one Q and that will take care of the charge and the uh, value plus Q. Knowing that Q is the electric charge, which I don't remember. I'm sure there's a symbol for the electric charge. The desired functional relationship, question mark here as well. The desired functional relationship. And actually, hold up. Let me check my, maybe this is something that she covered in class, the last class. I'll check my class notes really fast. And it's very complicated. Wait, back up and try this again. This is Rutherford scattering, by the way, what they call it. All right, I'll just try this again. We'll go back and see if we can get this. And maybe I'll try the book notation. Unless I can find a check. At least 1 sec. Let's check something really fast. Respond to something really fast. here. All right, let's try this again. Let's just start. Let's pass this. All right, now starting on page 109. The professor called it Rutherford scattering. Right. So again, this is the repulsive scattering of charges due to a Coulomb field, a fixed charge action on an incident particle. So to find another symbol, why don't we do this? Let's say fixed charged is the fixed charge is negative ZQ. Where Z is the magnitude and Q is the Coulomb charge or electron charge. And negative V eight the primes. When we say negative WQ is the incident charge. So where they have, hey, what's going on, Wilfredo? Awesome, Wilfredo. Glad you're here. Glad you enjoy the content. Thanks for letting me know. So we're doing some Rutherford scattering. It's a hard derivation and such. So the first time I went through it, I didn't get it. So hopefully today as I watch it while going through my professor's notes at the same time and using some notation that I'm familiar with. Hopefully I get it this time, so we'll see. Let me know if you have any questions. So these are the charters we're working with. So they have Z, E, and Z prime E. I have ZQ and WQ. All right, so we'll see how this works. So we know that the Coulomb force, which they're calling F equals K QQ over R squared, which we're now going to call VW Q squared over R squared. When I asked Professor about this, she said that the Coulomb constant Q will be absorbed into one of these other things, right? So now we have the repulsive or the attractive inverse square law, but now we're dealing with charges of the same type. So then we can look at the results in section 3.7. And in that section, we have a K. So this is what I believe they're referring to. I'll make this a bit shorter. Right, so we're dealing with inverse square law of force, right? So this is why we use in 3.7 because the R squared is in the denominator. And let me just make a side note of this. Section 3.7, we have F equals negative K over R squared. V equals negative K over R. And this was 3.49. And we have, I know there was another one that I saw. Oh, here, is this the, no, there's still 3.7. This is, that's not the one I'm looking for. There's an equation in this section that has just, well, I guess that'll do. I saw a more complicated one, but this one is actually better. We're looking at this right here. So going back to the section in question, that's why they're saying that K equals negative. So I'm going to use my notation. Negative Z W Q squared. And why is it negative? Because we have a negative ZE, a negative Z prime E. So multiplied together, we see they're positive in the F. So I guess he's just absorbing only one of the constants, one of the negatives in K. So that means that we would have F equals negative K over R squared. And that would be why. So the K is absorbing only one of the negatives, and we still have a negative on the outside, and that's why it's taking this form right here. Right? And this is 3.98. Let me see if Professor has something different on this point. Right? So she notes that the eccentricity is the same thing they mentioned. I notice she uses a little bit abbreviation. So we have the eccentricity. I'll go ahead and use the eccentricity equals square root of 1 plus 2e angular momentum squared over mass times v w q squared. So that equals, so since it's squared, you can remove the negative. So we have square root of, and comparing both the notes from class and the book, 1 plus 2e l squared over m a squared, because a is this, and it was squared, so we're going to remove the negative. So we have that L equals angular momentum equals m v naught s, and if potential equals 0 at r equals infinity, so we have two repulsing things, the closer they come together, the stronger the potential. So at infinity, v is 0. So E equals T plus V equals T equals 1/2 mv naught squared. Thus we have v naught equals square root of 2t over m, which is square root of 2e m. That means that L equals m square root of 2e over ms equals square root of m squared 2e over ms. So that equals 2 square root of side s square root of 2m e. L equals that. So E equals square root of 2e, and we're going to square that. So s squared 4 e over m a squared. So that equals square root of 1 plus 4 e squared s squared over k squared. So E equals square root of 1 plus 2 E S over K all squared. And then she went ahead and plugged in what K is. So we have square root of 1 plus 2 E S squared over, and K is ZWQ squared. And that matches what they have. And this is equation 3.99. Right? Then we have 1 over R equal. So we're going to go to equation 3.55. Like this. So R equals MK over L squared 1 plus square root 1 plus 2 E L squared over M K squared. Then we have cosine of theta minus theta prime. That's 3.55. Boom. So we have that. So what they're saying is if theta, so theta prime is chosen to be pi, periapsis corresponds to theta equals 0 at closest pass periapsis. All right. So I think this is where we need to see how this ends up at. So we'll follow what she has in the book. I mean, in the class notes, we have 1 over R equals MK over L squared 1 plus square root. Uh, I think I'm starting to see a bit something here. The first thing I need to do is equate these two things. I need to equate these two things here, this and this. So if 2ES world did we change that anyway? That was already there from the first part. Could have just kept that the same. Now, following the book, and they seem to be making things more complicated. So let me show you what I mean. I already have that E equals this, which equals this. And that equal as well. And all of that is equal, and it equals this. So right there, I could have, instead of them saying to input a swap for L in equation 3.99, that was already in the form that we needed without swapping for L. So all we have to do here is say 1 plus E cosine theta minus theta prime. And we can actually just go ahead and input the pi there right now. MK over L squared 1 plus eccentricity cosine theta minus pi. All right, so let's see what we do next. Looking through the class notes, all right. So this is saying that, what was it? The book says we have this. The condition is also that r goes to infinity. So that means that 0 equals m, and we know that there's a few things going on here. R is going to infinity. Still not seeing the detail that's going on in the change between these two things. Uh, K is M G W Q whole squared. Okay, so I think let's see what's going on a little bit more. So when she put in K here, she should put in the full K with a negative. So remember K has a negative on it. And the square just wasn't written too clearly. So it is negative 1 plus e cosine theta minus pi. And if we shift cosine by pi, so let's check this out. We have a cosine wave. It looks something like this. And this would be t a negative a. Um, this would be 2 pi. This would be pi. So that's cosine theta minus pi. So this is cosine theta. This is t equals 0. And if I shift this to the right by pi, t equals 0, t equals 0 for cosine theta minus pi. I shifted it the right way. So shift the graph to the right. No, have it. Well, it ends up being the same thing. But the negative would actually shift the graph to the right. So really we will be on the other side. I should have drawn my t equals 0 over here. This would be negative pi. This will be negative 2 pi, be 0. So shift the graph to the right. That'll be t equals 0 for cosine theta minus pi. So we see that cosine is negative. So maybe I wrote this incorrectly. Cosine theta for cosine theta plus 1 at t equals 0. So this is t prime equals 0. So, and we see that is negative because the graph shifted to the right. So basically that's like this lower part is now going to be at 0. So that's why the lower part is now at t equals 0, because the negative shifts it to the right. And so now we have a negative value for cosine. But that's the same thing as saying 0 equals negative mzw q squared over L squared 1 minus e cosine theta. Right, so now we have that. So if I distribute this negative n, that still equals 1 over r because r is going to infinity. So that's still 1 over r equals mvw q squared over L squared. I'm distributing this negative n. So then I have e cosine theta minus 1. All right, so now we have what the book has for what equation is that? 3/100. All right, so we have to get into the nitty gritty with some trig to make that work. Right, so we have this. And this matches what Professor has. This hyperbolic orbit equation has the same form as the ecliptic orbit equation, except for a sign change. The direction of the incoming asymptote phi is then determined by the condition r approaches infinity. So going back to the here, cosine phi equals 1 over the eccentricity. And how uh, fallback is in 3.94. So 3.94 is big theta equals pi minus 2 psi. Okay, so we have theta, big theta minus pi equals negative 2 psi. So psi equals pi minus big theta divided by 2. So we have cosine pi minus big theta divided by 2 equals 1 over eccentricity. So this is going to be cosine pi over 2 minus big theta over 2 equals 1 over eccentricity. And if we shift, well, the first thing we can notice is cosine is an odd function. So cosine of big theta over 2 minus pi over 2 should be the same. Like if I were to extract a negative from that, equals 1 over e. So if I shift this over, well, I can't put a negative in the front. It's odd. So if I put a negative in the front, it's the same thing. If I put a negative in the front, I distribute it, and then it becomes this. If I put a negative in the front, it's the old thing. And if I shift cosine by pi over 2, you can see how it becomes sine. So our 0 will be here. So this becomes sine big theta over 2 equals 1 over e. So we have that. And I think we're keeping up with the book. All right. So this seems to be the general reasoning. And again, to write that clearly, we have cosine of pi over 2 minus big theta over 2 equals cosine big theta over, well, I should wrote the whole thing out. They did it a different way in class. And I'm pretty sure this way is legal as well. They did basically negative sine and then distributed the negative, but I did a cosine and then shift to sine. All right, I think we're good. So professor then did E equals 1 over sine big theta over 2. E squared equals 1 over sine squared big theta over 2. And we're trying to get to this E squared cotangent ugly thing. So we have sine squared theta plus cosine squared theta equals 1. So 1 equals so whole thing up in it. So we have E squared equals sine squared big theta over 2 plus cosine squared big theta over 2 divided by sine squared big theta over 2, which means that E equals 1 plus cotangent squared big theta over 2. So E squared minus 1 equals cotangent big theta over 2. And I believe that's what they have. So this is in the book right there. And welcome who's watching. Let me know if you have any questions. I'll be on for probably 8 more minutes. Now I'm going to use equation 3.9 again somewhere. All right. This is why they had us do the uh, changeover earlier that I was saying we didn't need because we needed it later, even though I think that was a bad place to put it. But here I need to write a textbook, a scientific textbook. This. All right. So now we're going to plug that into the epsilon square and see if we get the same thing they got. And then I'll go ahead and call it. So E squared equals 1 plus 2 ES over Z W Q squared. So where they use Z prime, I use W. Where they use E squared, I use Q squared. All squared. So that means we have cotangent squared big theta over 2 equals, yep, no, hold up, squared, it's all still squared. Oh, that's right. We can take the square root afterwards. So tangent squared equals this minus 1. So it equals this in. The D1s cancel. And thus, if I take the square root of both sides, we have cotangent of big data over 2 equals 2ES over VW Q squared. This is in the book. So the desired functional relationship between the impact parameter and the scattering angle is therefore, so S, maybe that's the wrong one to copy. S equals ZW Q squared over 2E cotangent big theta over 2. So this is the one that we need to box. And I do have noted that professor said we should get, what was it? Need S in terms of theta. Need S in terms big theta. I forgot what S is. Let me remind myself. S is the impact parameter. I don't remember what the impact parameter is. All right, well, we'll do it. So I'll most likely be back. I'll go get a snack and need to make sure to get some sleep tonight. But I think I shall be back to go through some more of this so I can understand this before class tomorrow. And also have enough time to get some sleep. Our first class is at 11 tomorrow. So, but I still like to get up early. So we'll see. And I have some research to do as well. So I may actually work on that. So I need to model. I still haven't been able to adjust the chemical composition of the stars yet. I'll look into that some more. Maybe I'll do that when I get back instead of coming back and reading. And maybe I'll just read in the morning. I'll see how it goes. But I know I needed to do some research and do some modeling of this star. So maybe I'll do that when I get back. And I'll see how much time I have. Either I'll be back later tonight or tomorrow. But thanks all for joining. Like and subscribe if you haven't already. Help me get to 1,000 subscribers. I will see you all next time.